Hello and welcome to Cerebras Systems Customer Spotlight at Supercomputing 2021. I'm Rebecca Lewington, and I'm very pleased to be joined by Dr. Dirk Van Essendelft, Principal Investigator within the Advanced Computing and Artificial Intelligence team at the National Energy Technology Laboratory. I'm also joined by our very own co-founder and chief architect, Michael James. We're here to talk about the lab's mission to deliver solutions for an environmentally sustainable and prosperous energy future. Gentlemen, thanks very much for joining me.
Thank you for having me.
You're very welcome. So Dirk, first, tell us about NETL. What are you trying to achieve?
So NETL is the Applied Energy Lab for the Department of Energy's Fossil Energy and Carbon Management office now. So we are committed to providing the nation with clean, sustainable, reliable, and safe energy. Clean, cheap, reliable energy is the foundation and bedrock of a prosperous economy. And so it's something that NETL has been invested in for quite some time. And I joined the team here in 2008 as a computational scientist. And for the last, say, since 2012 or so, I've been looking at advancing our mission with artificial intelligence and machine learning technologies, hardware, and algorithms.
I gather you have a fairly aggressive goal to meet this decarbonized future.
That's right. The Biden administration has set forth a goal for the national labs to try and meet with a 2035 deadline to decarbonize the electric power grid and a 2050 deadline to try and decarbonize the rest of the economy. This is a really aggressive timeline, and will take a lot of innovation, a lot of development, and a lot of work throughout the entire sectors of the economy to try and meet these goals. And so that's why we're, as computational scientists, looking at the fastest possible methods to model energy dynamic systems. Because we think that we can support these goals by providing new tools that can do uncertainty quantification, design and engineering, and even help us develop fast-running digital twins that we can use to operate new power facilities that are cleaner and cheaper as we move forward in this new administration goals.
Interesting. There's a real sense of urgency in what you're up to. Michael, same question for you. What's your background and what's your role at Cerebras?
So at Cerebras, I'm a founder and also the chief architect of advanced technology. And of course, Cerebras is the company that created the world's largest and most powerful computer processor. I'm leading the effort to reimagine the algorithmic building blocks for the next generation of AI technologies. And prior to Cerebras, I was a fellow at AMD. There I pioneered a technique for adaptive self-healing circuits based on cellular automata. And we use this to create a fault-tolerant machine. I've always focused my career at the intersection of exploring natural phenomena, mathematics, and engineered machines. And this goes straight back to my academic background in molecular neurobiology, computer science, and mathematics.
Wow, I'm going to go with wow on that one, Michael. Thank you. So Dirk, can you tell us some more about specifically what you're working on now, and what's the impact of this work, if you're successful, well, you will be successful, what's the impact of this work on the goals of the lab as a whole?
Yeah, currently my main research focus is the development of math libraries for this wafer scale engine that you guys have been working on developing. And we want to be able to support extremely fast scientific modeling, as well as integrate artificial intelligence directly on one hardware platform. We're trying to do this to support the development of novel engineering systems to help support the carbon-free economy and improve energy security in the United States. If we're successful, we could reduce the time to solution for computational modeling by at least 2 orders of magnitude and decrease the energy consumption by close to 3 orders of magnitude. This has a drastic impact on the time that it takes to get engineering done It has a big impact on design and optimization and uncertainty quantification, and it can enable high fidelity real-time digital twin technology.
Wow, that's really interesting. Can you say a bit more about what uncertainty quantification is and why it's important in this space?
Whenever you model a system, there are a lot of assumptions and parameters that go into that model. And not only that, you're never really sure about what your initial conditions are perfectly or what the boundary conditions of the problem are. And all of those things have an impact on the result, right? And so what we need to do is not just like one model, but we want to vary all of those parameters and see how the system responds to varying all those things in a quantitative way. And so that's what uncertainty quantification means. And if you care to do that on a large engineering system, like what we do with energy conversion systems, it can take, you know, a month or more to run a single simulation on a supercomputer, depending on the allocation size, right? And so if we can drop that by 2 orders of magnitude in speed, that allows us to do what we used to do in a couple months, 2-3 months can be done in an afternoon, right? And not only that, with the model sizes that we typically do, we may be able to run more than one at a time on the Cerebras wafer scale engine. And so it really improves the productivity and enables us to have a much smaller margin of error that we need to live within, well, we know what the margin of error is to a much greater extent, so that we can live closer to the bounds that are what quote unquote dangerous, if you wanted to do that. But you know, when you talk about energy conversion systems, that's always, the efficiency is always at higher temperatures and higher pressures, right? And so you build in that margin of safety, and so the better your uncertainty quantification, that closes that window to the point where you can operate at a higher efficiency in a better conversion environment.
Trying to cope with more complex simulations and simultaneously drop the execution time by a couple of orders of magnitude. This is not a small task. So no. Can you say something about what the bottlenecks are, the traditional bottlenecks you have in HPC codes that are standing in the way of this?
I think it primarily comes down to two big things. One is communication latency between 2 nodes, right? So the way that we model things, we break space up into cells, right? So a little volume, and you have a cell here and a cell here and a cell here, and it goes in all directions, right? And you discretize your governing equations across those cells. So you do a Taylor series expansion, and you end up taking differences between these 2 cells to get slopes and, you know, all that kind of stuff. So there's, in traditional high performance computing, you know, you may have one CPU or GPU here, you know, literally like right here, and then, you know, over in this area you have another CPU or GPU connected via fiber network. And so the most stringent bottlenecks are communicating over that network. So the latency and bandwidth across that network are a big factor, especially in scientific simulations. It's the latency that's a big driver for how fast you can actually iterate in a loop. And I think that's probably one of the bigger advantages of trying to go to something like a wafer scale engine, because we take that latency, which is, you know, typically in the several thousand, tens of thousands to hundreds of thousands of clock cycles to send a bit of data back and forth on this network. It only takes roughly about 1 cycle on the wafer scale engine for a processor to access its neighbors. So right, just in that jump alone, you've gone from an iteration speed that is, you know, on the order of 20 to 30,000 iterations per cycle to whatever is theoretically capped by the clock frequency of the system running at. And, you know, you're typically running close to 1 gigahertz on modern hardware at 7 nanometers. So that goes from, you know, a theoretical cap of somewhere around 35,000 to something on the order of, you know, 1 billion iterations per second, theoretical cap.
So Dirk, you've been working in this field for a while now, and I heard you mention a few times some of the extraordinary goals you're looking at of accelerating the efficiency of your computation by 100 to 1,000 times. And I take it you mean both in terms of time to solution as well as the energy, the number of joules to the solution. And so I'm curious, when did you come to think that such a extraordinary goal might actually be possible to achieve?
Yeah, so I've been following roughly the news feeds and stuff like that about Cerebras, but I had doubted that I would ever have the opportunity to work on something like this, given, I mean, it's just such an extraordinary thing. But I happened to have a chance encounter with Andy Hawk at the AI for Science Town Hall in DC. And we met, and I told him what I was doing. And, you know, after hearing a little bit about the architecture, I intuitively knew that we would, at the minimum, see a huge energy savings because, you know, we're talking about reducing copper wire volumes and runs from, you know, millimeters to, you know, board sizes on the order of like this down to something that is nanoscale and transferring the same amount of data around. And so, you know, that's already in my head. I knew it was a several orders of magnitude change in the amount of energy to move things around. And also, you know, on the same token, the copper wire technology, as far as the length goes, it limits your bandwidth. So, you know, if we got the communication data pathways down to the nano or micro scale, like you do on the wafer scale engine, that the bandwidth should be very substantial. And so, you know, I kind of got the ball rolling with Andy there, and that's, he put me in contact with you, and the rest is really history here. So, you know, and it turns out, you know, with the SC21 paper, that we were really right. You know, we demonstrated for the first time an HPC calculation done 100 times, 200 times faster than what we feasibly could do with the physical limitations on a distributed system. And the energy savings was about an order of magnitude higher than that yet. And so, you know, this is when my management really got on board and started to push for a new type of developed technology on this. And when we started to really go towards more of a universal API that we could use in simple languages like Python to do scientific computing on. It turns out that this is a fantastic platform for solving field equations of just about any kind. And I'm just thrilled that this is working out so well.
That's very kind of you to say. So that leads me nicely to ask you, Michael, because you originally architected the wafer scale engine specifically for the linear algebra that's underneath all of this stuff that Dirk is doing. But did you always see the possibilities for HPC?
So we started Cerebras seeing that artificial intelligence is going to be a transformative, have an absolutely transformative impact across all areas of technology. And we were looking for the limitations, what was happening in current style computations versus what would you need in an AI paradigm. And we designed absolutely everything around that. So I can't say that we started with HPC in particular in mind, but it is the case that artificial intelligence and HPC have a lot in common. They are both really large scale numerical computations. There's algebra used all over the place. And HPC, you mentioned, we heard Dirk talking about field equations, and it's really the fact that that algebra and math that is pervasive all throughout science that is the sort of common linkage here. And we're seeing today in AI that these systems are being scaled up and up to the point that they're approaching the magnitude of even exceeding traditional supercomputers. So at the beginning, we looked a whole lot at the fundamentals. We were trying to find what are the drivers to make an efficient processor, what would need to change in this domain to make it sort of the future possible. And we looked a whole lot about information flowing over a 2D surface. Because essentially that's what we have. We're nanofabricating these processors. We have a lot of we have an area of silicon over which a computation plays out, and of course, there's information that's being exchanged. So we saw at the very beginning, to make these things possible at scale, you need to bring a whole lot of silicon to play. And if you look at all of the silicon used in a traditional supercomputer spread out over aisles of a data center, little tiny chips talking over these long distance connections, we know that is sort of the engine that drives all of this. We needed to consolidate that into an efficient, close proximity substrate, so that you could get an algorithm of your choice running efficiently on it. We saw the need to bring a whole bunch of silicon onto one computer chip, so that we would have really high performance computation at large scale, but on one device. And there's a whole bunch of information that has to flow over this chip, so that you're creating a large scale numerical simulation. The other thing we saw is that because artificial intelligence is continuing to be a developed field, that there's a lot of uncertainty about what algorithms people will want to run in the future. And so it was essential for us to create a fundamentally programmable part. And that's sort of where the design meets, because we were thinking about being able to sculpt information flows over a processor. And on the HPC side, where you're modeling physics, you have the differential equation specifying what that kind of information flow should be. That's why there's a natural synergy between these projects. Now, one of the primary differences that is still on the part is artificial intelligence is leveraging really imprecise numbers. That the field is going down from single precision, where it started, to half precision. These are 16-bit floating point numbers, and we see a lot of literature at 8-bit precision and even fewer bits in some work. On the HPC side, you see number systems that are double precision, 64-bit numbers, and I've even seen work going wider than that. And I think that this has to do with the different mechanisms that create stability in the algorithms that are used. So where you might use HPC to model what would happen if I flipped a coin in a tornado, where would that land? The AI system, maybe you would ask, what are my best top 10 escape routes? What was a good idea to duck and hide under something, or run for the trees? And so the different types of processing lead to different numeric requirements. I think that's an area where we will see ongoing work on both the AI and HPC sides.
Yeah,
Interesting.
I would agree with that. You know, that's one thing that I do appreciate about this architecture, is that we do seem to be able to write kernels that are very well engineered, based on 50, 60 years of HPC research and background and knowledge, but we're at the same time able to flip a switch basically and start using kernels that are optimized for AI workloads. And you know, so I think in the future, you know, the ultimate goal is not just to stop at scientific modeling, but we want to be able to do AI augmented scientific modeling. And so we want to be able to switch back and forth between modes of execution, where some of these things are AI driven models, like closures for drag and stuff like that are really difficult to derive from first principles for like really weird shaped particles. That'd be one example. But then at the same time, we want to be able to tell what the path of these particles are in a really detailed and meaningful way. And so, you know, the future looks like doing AI and HPC calculations at the same time. And oh, by the way, we don't want to move data around on and off the hardware, and as little as possible. Not until we have you know, some very high bandwidth in silicon photonics and all that kind of stuff. I think that when that gives us a little bit more freedom, but right now this is, I think, the best path forward that we've got.
It will certainly help, but you still have a small problem with the speed of light. Even the best photonic network can't go quicker than that. Michael, you wanted to add something?
Well, one of the nice things about the platform, and that Dirk is describing, we provide 850,000 completely programmable processing cores. They're arranged on a 2D mesh, and a key part of mapping the science problem onto the wafer is deciding where each component of data is going to live. So we have these systems of equations that they're processing data. It has to live geographically somewhere on the 2D surface of the compute engine. And but once you have that, what's interesting is the way that you lay data out to do the type of simulations that Dirk is running is the exact same data layout that you might use to train a neural network. So we'll be able to use the code that he's written to evaluate some system, some number of time steps into the future with all of these 3D little volume cells, having tracked the concentration and pressure of the model system, and then use that directly in place without moving it anywhere. So we're not even talking to the next rack, to the next computer system, not even the next core. Leave it exactly where it is, and now flip the program code in these cores to start training a neural network. Maybe this network's going to predict the future state of that system, and then once you're there a little while longer, go back into running more simulation to go forward. And so there is a world in which you have the complete synthesis of these two workflows.
That's right, and it's exactly like what you were saying, because if you look at the math to do an explicit time step for simple like a diffusion equation or advection diffusion equation, all it is a convolution, right? So if you wanted to go and cast this, in fact, there were some papers recently, that did this. You can use a convolutional neural network kernel out of TensorFlow to do scientific modeling under certain circumstances, right? If your grid is correct and all that kind of stuff. So the sparse matrix multiplications that are done are very similar in character, and the only major difference is that we do a lot more dot products in solvers, both to check residuals and tolerances. But you have the same type of reductions that must be done in neural network training kernels as well. So we kind of do the same type of math, but in different ways, different steps, I should say, in order to do solve a minimization problem and solve a linear set of equations.
Interesting. So just going back a bit, what you both said is that the big part of the speed up comes from simply the fact that the system as a whole isn't twiddling its thumbs waiting for data to finally arrive.
That's exactly it. Even
the fastest off-chip network is glacially slow compared to doing it in silicon. But enough theory. How does this translate into results for you, Dirk?
Right now we're at a research and development stage, right? So we're not actually modeling real systems, but we're building all of the evidence to support our continued development, right? So real modeled systems will come in the next couple of years. So what that means is, if for instance, like an ANSYS or a star CCM would want to be able to take a model of a new car or a plane or something like that, they would be able to use their existing front-end software and decompose it in such a way that they could solve the equations on this hardware. And so, what it means is it reduces design cycle time, and it increases accuracies, and it reduces costs, right? In developing new products. And so that's for the same reasons that we're interested in using this for, increasing the speed and the pace at which we do development for carbon management. The engineering world in a whole can take advantage of the same type of processes, because almost every product that you come against, whether that's a simple refrigerator in your house, or your car, or the plane that you fly to go visit in a conference, almost all of them involve at some point some level of CFD, or computer-aided design.
CFD is
computational fluid dynamics.
Okay, so what you're saying is you've got applications for this way beyond, you think, what you're actually working on for
that's right. Yep. So the kernels that we're developing could be picked up and used universally in almost every field of engineering that's out there.
Real-time CFD has been a pipe dream for the last few decades. So
yeah, that's right. I know of one study that was out of University of Pennsylvania. They were a DARPA funded project, and they were trying to design an in-flight CFD-based controller, right, for a helicopter to land on the deck of a pitching and rolling ship, right? This is something that's really difficult, right? And it's really difficult to have an automated computer system flight controller do, because it can't take into account all of the variables that happen with buffeting around the ship and turbulence and all that kind of stuff, right? So they tried to simplify everything that they could, and they ran it on their cluster at Penn State, and it was like barely qualifying as fast enough, right? And so then all of a sudden you also got, you know, a computer that's the size of a house, you know, that has to sit, you know, somewhere with data moving back and forth, you know, to a flight controller, right? Whereas, you know, some version of this kind of technology where, you know, we've got the computing power of our, you know, Joule 2 supercomputer, you know, that is literally the size of a house and consumes as much power as a small industrial facility. You know, you're now taking that and shrinking it down to the size of a dorm refrigerator, and, you know, running it on a power budget that's, you know, about as much as your home air conditioner, you know, takes. And so the order of magnitude changes in scale in that, not only with the speed, but also the energy efficiency, size, and weight, mean a whole lot of new applications where we could use scientific modeling to back up new applications, right?
You could put this thing on a ship.
You could put it on a plane. You could put it in a helicopter, and it would likely fit within the power, space, and weight budget, you know, of some naval, you know, aviation system, you know. So the applications are, you know, for this kind of stuff are not even imagined yet, right? Because this hasn't even been a thing for more than a year or so.
That's amazing. Exciting.
But when we think of supercomputers, I think everyone's mind goes to the data center, a warehouse-sized machine, exactly like what we've been talking about, that is far away from the site of the application, that for some reason is usually not running any kind of real-time program code. It is something where a team or researcher has to check out and reserve time on this thing. You get scheduled, your job is running. And so I guess we've wondered, does real time have to be anathema to supercomputation? Is it no longer a supercomputer if you can mount it on the airplane?
Yeah, I mean, that's the hope. I mean, you know, in our particular application, you know, we want to be able to integrate this into every modern power plant, and be running a digital twin, basically. So, you know, a typical power plant will have, you know, several hundred, several thousand maybe temperature sensors throughout the system, on the order of a few dozen, you know, concentration measurements throughout the system, and on the order of a few dozen flow controllers, right? And that's all data that is, you know, we have access to in real time, right? And so if we have a fast running digital twin that can run at that speed or even faster, what that allows us to do is figure out control pathways that would help us to do load following for greater renewable integration and maintain stability and security on the power network, right? And so that's why this stuff is so powerful, right? And can make such a difference, because we need systems that can be more dynamically responsive in a new energy environment that has a lot of renewables on it, right? Because everybody knows the wind doesn't blow and the sun doesn't shine all the time. And, you know, we're not to the point where we have exhaustive, you know, backup power that's not, you know, tied to a solar or wind generation system, right?
You're talking about not just making one power plant work, you're trying to make an entire smart grid work in a way that's resilient and robust. And we don't even have a dumb grid that does that at the moment. So that's a huge step you're trying to make. Yeah, yeah. But none of it was even a possibility. Nobody really even thought about this kind of stuff, you know, much past a year ago, at least not with high resolution modeling.
We had the ability to do what we call reduced order models of different types of systems, but you sacrifice a lot of accuracy. And if you start going outside of your design envelope in that thing, that you can get results that are not meaningful and maybe even dangerous as far as a digital twin is concerned. But now we have high resolution information, high fidelity information that can be processed at or faster than real time for the first time. So, you know, it's going to take a while to get deployed on something like this. But what that means is that, you know, every plant in the United States could have a digital twin with something like this running on it that would allow us to pick control paths. And then we could have these network of reactors speaking to each other and integrated with weather models, so that we could predict, you know, okay, we're expecting, you know, the sun to stop shining at this time, and the wind to stop, you know, producing, you know, being able to produce electricity at this time. You know, let's figure out a predetermined control path with uncertainty built into it, so that we can more readily respond to the dynamics of the Earth system that's really tied to renewable energy.
So are you saying that the digital twin sort of exists just in a future from where the real systems are?
Yeah, I mean, literally, like somebody would take Cerebras Systems or some other, you know, similar technology and install it right at the plant, right? And they would have this model of their plant running, and you could literally change the boundary conditions in time to respond to what the plant is either doing, or you could use it in a uncertainty quantification where you could try and set an end goal. Like, I need to bring up my power production by this time, and I need to figure out what's the control inputs that need to happen to bring it up to that at that time, but do the least amount of wear and tear and damage to the plant, right?
That's amazing.
This is great to hear you talking about, Dirk, because we made this processor not to make an incremental impact on the world, and what you're talking about is sort of a transformational deployment, that you have a new compute capability, and you're looking to ask what is unlocked, what fundamental difference can we have in the way that we run the nation's energy grid.
Yep.
Yeah.
So you know, I kind of see two halves of the two sides of energy utilization. On one hand, you have, before your facility is built, you need to do a whole bunch of computer modeling to try and understand how you expect the system to behave, right? So, you know, that's one side of things, right? That's kind of the way we try and use HPC now. But even like the HPC speeds are so slow that it really even precludes its own use as a good tool for that, right? So it's an enabling tool on that side that brings down time and costs for development. But on the other side of the coin, you have, once a plant is built, you know, can I do more with this plant than what I had expected to be able to do? And so this is where those digital twins come in, because you can answer those questions with a high degree of certainty and a high degree of fidelity, right? To know, am I going to exceed a safe, you know, temperature in a certain spot? Like, I don't want to blow a hole in my steam tubes, you know, throughout the entire process of trying to change state here, right? So can I pick a control path that gets me to a new state, a new operating level in a certain amount of time? You know, that's a big challenge, right? And that's why we have things that are divided into what we call base load power and peak shaving, right? So base load, you basically operate the same all the time, right? It's always producing 1.3 gigawatts of power or whatever it is. And then you turn on peak shaving plants, you know, natural gas that can spin up and down. But we want to make these kind of base load power plants more dynamic, so that we can extend the range and safety that we can operate with renewables on the grid.
And I want to pick up one thing you said to me when we chatted before this call, is that there's a possibility of improving the security of the system as well. Can you say something about that?
That's right. So if we if you look at, we call this cyber physical security, right? And so if you kind of look at what happened with Iran's, the destruction of Iran's centrifuges, right? It was called a Stuxnet worm, which is basically a virus. And somebody got in there, and this thing changed the output of these controllers that were spinning these tubes really fast, and broke the tubes basically in a catastrophic way. And while kind of spoofing real data signals so that nobody knew what was going on, right? So if you have a good digital twin for a power plant, you can try and detect either when a particular controller starts to fail, or somebody tries to mess with your controller without your knowledge, because you'll see dynamic responses in other parts of the system that this controller or person trying to get into the controller won't have necessarily control over, right? So you'll be able to detect when someone is trying to mess with that system by the overall system response through this digital twin. And you may even be able to isolate where you think the problem is, so that you can go and respond more quickly and get back to nominal operations or expected operations.
So the digital twin is actually, in a way, the reality now, to give you a reality check on what the physical system is.
Yeah, it is another tool to use for reality check. And digital twins are also useful. I mean, when we talk about energy system dynamics, again, I had mentioned that we're in high temperature, high pressure environments. It's where we make the most efficiency for thermal energy conversion, right? Those are extreme environments. It's difficult to take measurements, right? It's difficult to actually know what's going on, outside of wherever that little point is that you put your thermocouple to measure temperature, right? And so another good use of digital twins is to give you a better operating picture, to know, like, okay, I have a hot zone, but if I change this, my hot zone starts to grow, and I can get some relative measure of confidence about where my hot zones are and keep it safe, right?
But of course, none of this is possible without making a huge step change in the compute resources you have available to you.
That's correct. So we have we have two possible pathways forward, both of which could benefit greatly from this. One of which is greatly accelerated scientific modeling, which is what we're primarily focusing on. The other is physics-informed neural networks, right? Of which training is paramount, right, for us. And so both of them can be used in appropriate environments to give us a picture, both in space and time, of a physical dynamic system.
Physics-informed neural networks. That's a great phrase. I'm going to remember.
Yeah.
So just to finish off, blue sky question, Dirk. If you had unlimited compute resources, what would you do?
I'll answer in two parts. For work, I would create this power plant network that we've been talking about. I would put a local processor in at every power facility, and then I would tie them together with real-time data. And then, I would use a supercomputer, probably of a bunch of different wafer scale engine type technologies tied together, so that I would have an Earth systems dynamic model that I could overlay on top of all this, so that I could make something that was really secure and reliable, so that we can avoid some of these issues that we were like seeing in Texas this past winter, where we saw power security issues, right? But I think, if I were to somebody were to give me a few $1 billion to invest in unlimited computing hardware for me, and I had to still solve a scientific problem with that, I think, I've always been interested in cosmology and astrodynamics. And so for me, I think, trying to understand how the universe evolved and answer some of those really big questions about what is dark matter and dark energy would be just, absolutely fascinating for me personally. But
well, we'll see what we can do. Michael, how would you answer that question?
Well, now is a really special time for computer scientists and data scientists. We all of us have access to nearly unlimited amounts of computation. And it's one of the goals of our field to see in artificial intelligence, can we understand the computational basis of intelligence? And what's special right now is computers have crossed a threshold where a very simple learning rule is possible to show that it yields real insights just by running at tremendous scale and processing real world data. And as scientists, I think we want to use this growing computational ability to continue understanding how this phenomenon of intelligence works. As technologists, the stuff that Dirk is talking about, we'd like to discover what new possibilities arise in the future as we integrate AI and technology.
Excellent. Well, I think that's a brilliant note to finish this chat on. Gentlemen, thank you very much for joining me. This has been amazingly interesting, and I'm sure everyone's going to agree with me that this is amazing. So thank you very much.
Thank you.
Yeah, thank you for having me. Appreciate it.